I'll give you a quick little if-then recipe for deciding what to use. So there's three basic things you can do that are kind of like, come on, get bigger for me. There we go. Oops, a little too big. There we go. Okay, so you can fork a process, you can spawn a new process, or you can use multi-threading. And so async is in this multi-threading category, so that's what I'm gonna spend most of my time on, but just so you know about the others and know when to use them and when not to use threading, I'll talk about those as well. So there's this function called os.fork in Python. Forks are kind of a sore point for Python because of the GIL, but they are fast because you do not have to spawn a whole other Python interpreter, which is what you have to do for the alternative. But they are a bit unsafe. You have to be very, very careful about, because they're both, actually, I actually don't know why they're unsafe, but you should be careful about them in terms of memory safeness. It's one of those things that you have to watch out for in terms of your code being vulnerable to memory overruns and those sorts of things. Bloated because it creates a copy of everything in RAM. So it'll double the use of your program, everything, even the code that's already passed. So what os.fork basically finds a point in your code when you have this if statement, basically this fork statement, and your program is duplicated and then proceeds around along both of those paths simultaneously in two different Python interpreters. So it's like you created two Python interpreters and you started them up both at that point in the program. Does that make sense? That's what forking does. Spawning is when you actually launch a new Python interpreter with a new subset of your current program to run in it. And so this is great for CPU bound tasks where you got a lot of computation you need to do. So like machine learning model training, once you've got all the data loaded into RAM, once you've got all the, everything you need is in RAM and you don't have a lot of IO to do, and you just need to do a lot of math on it, then spawning or multi-processing is a great way to do that. Multi-threading. This is great for IO bound tasks. So this is not when you have a lot of math to run, but you have a lot of stuff to read from disk or from a network process. In fact, the library that you import is called async IO because it's all about doing asynchronous IO communication. So you can have one thing going out there and reading from the internet and another thing doing computation. And to simulate that, I'll just use a sleep task so you can see what happens when you have multiple things going on at once. By the way, don't try to do this in a Jupyter notebook, because Jupyter notebook is already using threading. I'm sorry, async IO underneath the hood. I think each one of the it's using threading. So those terms are synonymous. Multi-threading, threading, async IO, those are all mean the same thing. When people say those words, they mean the same thing. And so in Jupyter Notebook itself is using threads to manage each one of those cells in your Jupyter Notebook. So if you go in there and try to create your own threads, it'll get all borked up and it tells you so and an error message. So so instead, but you can use IPython, which is the equivalent of Jupyter Notebook without all the cells and graphics and serving up of that in an asynchronous IO bound process, because it's a web server and so there's IO happening, and so they use, and that web server is running asynchronously. So you have multiple different threads working on that same process. By the way, when you do threading, you will not see a new process pop up in your HTOP or top. It will still be running on that same core, on that same CPU, and in one thread. So you can't really speed up your computation. So you only want to use this when you're waiting around for something else to happen somewhere else. When you're trying to spread your computation out across the internet to somewhere else, where somebody, or you're trying to wait for something to happen in terms of reading something off the internet or trying to read something off a disk. Okay, so let's do a quick example. We'll start with the simplest possible example where you just got to sleep. And here we go. So first you have to import async IO so you can have this this run method. So you create your coroutines first, and so this is a coroutine because it has this async before the def in it. So this creates a function that doesn't run until you tell it to run. And once it does run, you can have multiple ones of those coroutines running in parallel if you want. I guess this really isn't. I'll show you what a real coroutine looks like. This somebody out there who knows better than I do, who uses these a lot more than I have, would probably say, "Hey, that's not a coroutine." But anyway, it's an async function. So so when you run that, you can see that the sleep happens, and it came back in about a second. So this behaved like you would expect it to in a normal function, but where the only difference is where this can happen, you can have multiple processes doing this. You can have one thread, I should say, waiting for sleep, and another thread waiting for another sleep, and they might come back at different times. You can think of asynchronous as like the asynchronous communication you're having on Slack, where you can be waiting around for somebody else to say something, while you're also waiting for somebody else. You can have two conversations with two different people. And so that's what this next example will show you. You can imagine you've got these two different tasks you want to run, and I've put them both inside. So I've created two await calls, both inside of the same other asynchronous function. And so the awaits are going to happen simultaneously. Actually, they're not. They're going to have, because await causes them to happen synchronously, and I'll show you the code that makes them happen asynchronously in a second. So these will happen serial, and you'll see it in the output. So you started the whole process at 5542, and it started the first job right at that same point at 5542, and it's gonna finish its job in 1 second. The other person didn't start until the first person finished their job, and that person finished 2 seconds later at 45. So they all did their sleeps in series. They did not do it in parallel. So now let me go to the example that does it. This is the lack of prep. I haven't run this other one yet, and hopefully it will run. And this is straight out of the Python documentation. So if it doesn't run, you don't get to blame me. You get to blame Python docs. Let's see what this one is going to do and how it's different. Is it different? It's still got the two awaits. Actually, I don't think this is any different. I think I haven't copied the same thing. Let's find the right one. Maybe this is it. Both have awaits. I'm looking for create task. This is the thing we want to do differently. Let's see if that one if that did what we wanted it to do. No, we didn't do the create. So this is the thing that's actually creating a good coroutine. So when you do this async io.create task, that's creating a coroutine. So let's run this code and see if we can make both of those things happen in parallel. Both of those, oops, that's not it. Why? Oh, I didn't highlight anything. Hard to tell. Okay. Now I don't even know. Maybe I have to say async io.run main. Probably so. I should check the docs before I run it incorrectly and blame somebody that shouldn't be blamed. They don't tell me how to run it. Maybe I'll do it this way just to make sure. think
Yeah, I
that's the
think
way
that's
we're supposed to run it. Okay, so what happened here, and I wish I'd had the time to edit their example and put in these times on those other, the hellos and the worlds. But what happened was this first one started at the very beginning at 09, and it waited 1 second. The other one also started at 09, and it waited 2 seconds. And so 09 plus 2 is 11 seconds later. And so they both ran in parallel. Both, you can think of that sleep as waiting for IO communication. So you can see how this would be useful if you had 2 different files you're trying to read, or 2 different network API calls you were trying to make. They would both be able to do their job in parallel, or at least siphon in some data. And you could be doing something else while you're waiting for those 2 things to go on in your processor. And then once they got done, then you could go back to whatever you needed to do with that data you were pulling in. So that's all I have on async IO and asynchronous tasks and what they're good for. And the basic algorithm in choosing when to use these things is, if you have what's called an IO bound task, use async IO and these techniques I just showed you using awaits. And that's what we're doing for the Discord bot. And that channels thing I talked about last month, async and await are the key things you did over there. And you're also inside of the PyCord package. They're using channels, WebSockets, and async IO to manage the connection to Discord. So you get real-time communication of everything that happens on Discord to your bot. So you can react to it just like a human and participate just like a human asynchronously with everybody doing their thing on Discord. So that's a great application for it. I could show you the code for that if after we're done with the talks. So if you have an IO bound task, use async. If you have a CPU bound task, then you're going to use either of the other 2 things. Multi-processing is probably your best bet if you have a CPU bound task, because that's going to spin up a new CPU somewhere and do some work for you in parallel on that math. Be real careful about using the other one that I mentioned. It's unsafe, and it doesn't really gain you a whole lot in terms of CPU for the overhead that you have to spend on it. That's it. I'm still a newbie at this.
Very well done, Hobson. Question, what do you consider a CPU-bound task that would be more appropriate for spotting or spotting a thread or forking a thread?
So that's something like training a machine learning model once you have all of the data you need. So like in Sebastian's case, when he's training a paraphraser, he has all the paraphrasers all loaded up in RAM in some data frame, pandas data frame, or Python list. He can iterate through that using multiprocessing. He have 2 different processes training on 2 different subsets of the data, and actually that's a hard example, because then you got to merge the answers that they both got for the appropriate weights. And I think there is a way to do that, because that's how most training is done. Or if you're doing some graphics rendering, like if you're trying to render some new 3D models for a video game, multiprocessing would work well there. You could have one process rendering one element in the system, like one character moving around, and then another could be rendering another character moving around, and they could all be on different CPUs running in different processes. Does that make sense for CPU-bound tasks?
Yeah, it does. I've also read, although I haven't done this personally, but I've also read that for very heavy computational tasks, sometimes using multiple cores can help.
Yeah, you're exactly right. That's what I was trying to come up with in my mind, some computation intensive tasks.
Most pure Python code will not use multiple cores, but multiprocessing can do that, but also C modules that aren't bound by the GIL can also do that. So like NumPy can use multiple cores.
Oh, yeah, right. So when you do those vectorized operations, like you say, one vector multiplied by another vector, yeah, you're right. It'll spin up all, 16 of your cores if you got 16 cores, and they'll all do one small batch of those multiplications and then combine them all together in the end. Forgot about that. Thank you.
Is that just with regular NumPy, or is that with some add-on?
Straight out of the box. You can watch it happen when you do a multiplication on your HTOP.
Yep.
The part of NumPy has to be optimized in order to do that, but most of NumPy is, I understand.
Yeah, multiplications are definitely optimized that way.
Yeah, another use I've seen for threading is actually in Python game development using stackless, where you run a whole bunch of microprocesses as different threads. But I would hate to see the hardware that runs that. It's got to be like water cooled, ridiculous amount of hardware.
Cool. I'm not familiar with that package.
Any questions before we move on? Sorry, I didn't want to cut anybody off.
So if a user is getting into this and feeling they have a need for it, is there some kind of benchmarking that goes into this? Like you echoed out the date to the milliseconds, and then you would use async, fork, or what was the third one? And then see if those times improve, I guess, when you rerun it?
You usually are working on a problem. So you're building some bot that's interacting on Discord. And so you use it without threads and you see how well it does and all the different behaviors, the delays between when somebody says something and maybe you're doing polling or something, and whatever it is, there'll be some sort of behavior that you're trying to improve. And so you'll figure out, you'll have to that's one of the key things about async and threading is you have to know what you want to happen when and where, and you have to schedule it in you have to decide, you have to create those coroutines and break apart your code into bite-sized chunks about what you want to happen where's your IO really binding you up that you need to create a separate task for it. And if you can do that and you have an idea of how to do that, then you'll go implement it and you'll see if it improved your particular problem, because everybody's problem is different. Everybody's internet connection speed is different. Everybody's disk speed is different. Sometimes it's the right answer, sometimes it's not.
So there's a certain amount of tuning and testing, but you have to be careful, similar to Linux and Unix, like priority and nicing. You don't want to interfere with the kernel and how many threads.
You don't have to worry about that with threading. You've got complete control of that core that you're doing the threads in. So you don't have to worry about nice or prioritization.
Okay.
You have complete creative force, and you all to create a really optimal bit of code or create a completely suboptimal bit of code. It's entirely up to you and your design of what you make asynchronous and what you don't.
So if you run a default Python program, it has those threads at its disposal, but it's not using them unless you tell it, hey,
yeah, you have an infinite number. It's just like having an infinite number of functions. You can write an infinite number of functions. And so you can create an infinite number of threads. It's just, do you want to?
There are drawbacks to very large numbers of threads.
Yeah, I bet there are.
Yeah, you can make that the operating system's problem, and the operating system has a very large hammer to kill threads, and they may do it without your permission. So if you don't have a thread-safe program running in those threads, you got problems.
Yeah, they usually won't kill the thread. They'll just kill the whole process.
Did your examples necessarily have to do with parallelization, or just running a single thing at a time faster?
It is parallelization, but not in the way you think. All of these are under the heading parallelization. These are all different ways to have different stuff happen in parallel. But the difference is you're not doing computation in parallel on your machine with async. you're doing communication over the internet. Somebody else's processor is running in parallel with your processor. That's the only parallelization that's really happening. You're not really doing anything in parallel with threads. You're stuck with, it's actually just time sharing that. So when you say sleep, it just stops using the processor, that core, that thread, just it stops running essentially, and it comes back to it when it actually has some work to do, because you've scheduled that in the async in the way you called those functions. So it's not actually running things in parallel. It's just skipping back and forth. It's just like your brain. You only have one place you can focus your attention, and you can shift it from one thing to another. And if one side of your brain is listening to somebody talk and they're talking really slow, they're spitting out one word and then pausing for 10 seconds and spitting out another word, then you listen to that one word, and then you go listen to the other person and their word, and then you go back and listen to the other person and their word, and you go back and forth, but you're not doing it in parallel. You're just taking advantage of those other two people's slow processes and to speed up what you want to get done. Does that make sense?
Yeah. So is another part of this to look up the specs of your CPU or your server's specs before you do this, or doesn't matter?
It's all just paying attention to how your program is running. And if it's doing the behavior you want, then don't do anything. If it's not doing the behavior you want, and you think that this is a tool that can help you do that switching between different things that are happening, if it's IO bound, if you're waiting, if one of the main things that's holding you up for doing something you want to do is waiting for the disk to be read or waiting for some data to flow down from the internet, then there's probably a way to speed that up or make your program run better and have a better user experience if you have async IO working for you. Another example would be like that little spinner you see in a web page for while it's waiting for something to download or whatever. That's an example of, you have a little animation, you have something else happening in parallel with that that download of data happening. And you could be doing something completely, the user can go on about with their task. You can continue to serve up the user interface. And then once that download is done, you can let them know and they can deal with it. Does that make sense?